Hi, my name's Tanish, and I'm going to be presenting my final walkthrough for my CSC209 shell project, my SH. This shell supports interactive commands for parsing, job control, signal handling, piping, environment variable expansion, and a full TCP client-server chat system. Let's start by compiling the project from scratch. So to do this, we're just going to run make clean, yeah, just to make sure everything's clean, and then make. And then you'll see our compilation succeeds with no warnings or errors thanks to the strict flags in the make file, like wall, werror, and fsanitize, as you can see on my screen here. Okay, so now we're just going to jump straight into the background processes demo. So I'm going to begin by launching a job. So I'm going to do sleep 5 ampersand, and then I'm going to do sleep 10 ampersand. And then what I've done so far right now is I've launched two background jobs with the ampersand, and the shell assigns the job numbers and PIDs and prints them just like in Bash. And after waiting 5 seconds, you can see that it has finished, done sleep 5. And when I actually kill the job, you'll see I've actually sent the kill command to send the signal. And when the job finishes, it is killed and it prints a done message and it reclaims the memory as needed. So now I'm just going to do a little bit of a code walkthrough and explanation on this. So basically just explaining the signal handling and overall the job cleanup. So we're going to take a look into my sh.c, and in the main function, you'll see that I registered the sig child handler using sig action. And the handler itself is pretty simple. It just sets a global volatile sig atomic underscore t flag called bg underscore flag. And what this does is just avoids doing any complex work inside the signal handler itself, which is important for safety. In the main shell loop, I call check underscore bg underscore processes. And I do this basically before and after each command to see if any background jobs have finished. All right, so now we're just going to take a look into the built-ins.c file, specifically the check underscore bg underscore processes function. So you'll see a line of code here that says PID underscore T result is equal to wait PID. I'm passing the PID, the address of the status, and the W and no hang command. So you'll see here I'm using wait PID with W no hang to non-blockingly pull finished non-blockingly pull finished child processes. If one finishes, I print a done message in this format. So in this example, it was square bracket 1, square bracket close plus done sleep 5. And after doing all of that, I free the job's memory and update the background processes list. So if we looked into the built-ins.c add background processes function, when a job is when a job is first launched in the background, I track it using a linked list, and each entry stores the job ID, the PID, and a copy of the original command string. And what this does is it allows me to identify and cleanly display which command is finished, even if the user has entered more since. In terms of design alternatives, I considered using the signal FD function and a dedicated thread to receive signals through a file descriptor. This would just allow for full decoupling of signal logic, but it does add a lot of complexity and thread synchronization risks. So the current flag-based approach is simple, safe, and effective, which is perfect for an interactive shell. Okay, so now moving on from this, I'm gonna move towards the networking demo. So I'm gonna show how the server and client interact with each other, as well as how it deals with long messages. So to demonstrate some simple networking functionality, I'll open one terminal for the server and two for the terminals as clients. So in my first terminal, I'm just going to start the server. So you can say start server 444. That's the port I'm using. And in terminal 2, I'm going to connect. Oh, yeah, so it seems that I messed up. Sorry, the port wasn't available, so I'm just using port 446 instead. Now in terminal 2, I'm just going to connect to this port, and that's going to be my first client. And in terminal 3, I'm going to have another client, which is going to be client 2. And now when I send messages between the clients, you'll see that it is working like a chat. So I can talk So yeah, you'll see I'm from client one, I'm saying hi, and then you can see that in client two, and then vice versa as well. So now I'm gonna send a long message from client one to test buffer and broadcast handling. So this is a very long message designed to test how well the shell handles blah 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 blah. So if you see how it's done, the full message is broadcast to all clients and to the server, and there is no truncation or crashing as expected. Okay, so I'm just gonna do a code walkthrough of the behaviors that are going on in the networking and long message handling. So we're gonna go back into built-ins.c, and we're gonna specifically look at the server loop function. So my server runs in a child process after start server, and the parent stores its PID, and the server uses select to multiplex between client sockets and the listening sockets. So when a client does send a message, I use rec v into a 1 kilobyte buffer, and this is just done using a character array, and then storing everything like so in the code. So you see I write char buffer 1024, and I write int n is equal to receive v fd buff size of buff -1, 0. So I make sure to null terminate and prepare the client ID by using sprint f or sn printf. Then I send this message to all connected clients and write it to std out. And some of the edge cases that are handled here is that if the message is / connected, I count clients and respond with the count only. And I also ignore sigpipe to avoid crashing when writing to a disconnected client. So the pros of these design choices are that it's fully non-blocking via FCNTL function, and broadcasts are efficient and easy to trace. It also supports up to FD_set size clients. So some of the cons is that message over 1024 bytes will be split if no new line is present, and that there's no custom message framing or reassembly, which is something that could be improved down the line. All right, so to wrap up my video and give a conclusion, in this walkthrough, I've demonstrated the core features of my shell, including compilation with no warnings, background job management and the done messages, signal handling via sigchild and job tracking, built-in and external command execution, TCP networking with and finally TCP networking with message broadcasting and client counting. I also walk through key parts of the code base and explain design decisions, including how I balance simplicity, safety, and scalability in handling background jobs and networking. Thank you for watching.